Hey there, welcome to comp111. Today's lecture 8 and this time we've got a packed one. We're going to build merge sort from scratch, understand why it's so much faster than anything we have seen before, and then apply divide and conquer to recursive data structures like nested dictionaries and file systems. How do we measure time in Python? So essentially, before we can get into sorting, we need to first learn how to actually measure time and how fast our code runs. Just saying that it felt slow doesn't really teach us much. So Python uses this something called the time module. Think of it as a stopwatch. So in line number 3, you record the current time, and then you run whatever you want to run, whatever you want to measure afterwards, and then you measure the time again. So the difference between the final time minus the start time is going to give you the total elapsed time for that algorithm. So this is in seconds, by the way. And that's really all there is to it. Time function returns the current time as a float, and the difference gives you the elapsed time. So here's a quick example. On line 6 and 7, we are summing 10 million numbers in a simple loop, and we're timing the whole thing. On my machine, it takes roughly about half a second. Not bad, but let's see if we can do better than that. So same problem, two different approaches. Lines 8 and 9, these ones, these are the this is basically the loop that we just saw. Then in line number 15, we use the math formula to for the sum of first n integers, n times n, this should be plus n plus 1, and divide by 2 to get the same answer in a single operation. Well, I guess 3 operations, but it's still much faster as compared to n operations that we do in the loop above. So two different algorithms, but the end result is exactly the same. So take a guess, which one runs faster, algorithm A or algorithm B? The loop takes a half second, as we saw, and the formula takes essentially pretty much 0 time, right? It's instant, and we are talking about millions of times faster for exactly the same result. So destination is the same. One walked, but the other teleported, and that's why algorithm choice matters so much. So the question is, why are we about to spend a whole lecture on sorting? Because sorting is literally everywhere around you. Instagram sorts your feeds by relevance, Spotify sorts songs by artists, Amazon sorts product by price, your email is sorted by date even. Netflix alone sorts watch histories for over 200 million users. And this is not some textbook exercise, Sorting is one of the most fundamental operations in all computing. Let's put two algorithms in a race. On line 3 to 11, we have selection sort. This one. And that is a naive O(n) squared approach. And on line number 21, we have Python's built-in sorted function, which sorts the data. Now, the thing to note here is selection sort on just 10,000 items takes a few seconds, but sorted handles 100,000 items. That's 10 times more data in a fraction of the time. Now, the fun part is Python's sorted function is implemented using something called a tim sort, and which is essentially actually a variant of the merge sort that we will be building today in this lecture. Let these numbers really sink in. At 1,000 items, selection sort takes about a second, while merge sort finishes in 100th of a second. Both feels really fast enough because the data is small. But at 100,000 items, selection sort takes roughly, let's say, 3 hours, and merge sort is going to do it within seconds. And what about million items? Well, the story goes to beyond days, essentially. So if selection sort takes 12 days, merge sort is going to handle that within a second. So that's the kind of differences that we are talking about here. That's the difference between O(n) squared and O like n squared and n log n running time, and exactly why we need smarter algorithms. Divide and conquer, we did that in the last class. So let's do a quick little recap of the divide and conquer recipe. There are three steps essentially. One is the divide, that you take your problem and then you split it into roughly equal pieces. And then the step two is conquer. You solve each half recursively, and then in the combined step you merge. Let me actually, yeah. So in the combined step you merge the results back together. We have already known the binary search, which has a clever divide step. Merge step cleverness is going to be in the combined step. So let's put them side by side. Binary search divides by finding middle, conquers by searching just one half at a time, and combined step is basically nothing. You just return the answer. On the other hand, merge sort divides by splitting the list in two halves, conquers by sorting both halves, and then all the hard work happens in the combined step, merging the two sorted halves into one. So the binary search is clever about dividing, and the merge sort is clever about combining. So yeah, you can see that here. Here's a thought experiment. Imagine that you have 8 shuffle cards, and obviously, as you can see, that they are not sorted. How do you sort these? So basically, the naive approach is that you find the smallest item in the list, you scan all the list, and then you pick the smallest item from there, you put it in the first place, and then you go to the next item, and then you compare it with all other items, and then find the smallest one, the next smallest one, and then you put it in the second place, and you search for the next smallest one and put it in the third place, and so on. So you keep on doing that, you'll get a sorted list. So basically, this is comparing everything with everything else. A pretty inefficient n squared algorithm. This is not what we are looking for. How about this? If we split 8 cards into 2 groups of 4 cards each, you sort each pile and then merge them together. Now you just merge everything back up, and you're done basically. And also one note that merging two already sorted lists is much easier as compared to merging two unsorted lists to get a sorted list. So that's the trick, that's the key piece of the puzzle here. The merging of two sorted lists to get the final larger sorted list. So just like they say in real life, keep ignoring the problem until it's sorted itself. Moving on. So how merge sort actually works. Let's see the full picture here. We have a list that has 4 items. First, we divide or split it into 2 pieces with 2 items each. And then in the other next recursive step, we divide each of these lists into further 2 sublists. But at this point, each list is a single item. And we know from the base case that single item is already sorted. So what we do is we are now ready to merge these single items together. So basically this list is sorted 38 and this list is sorted 27 because that's a single item. So how do we merge two sorted lists here? Since there are only 2 items, we compare 28 by 37. Whatever that is smaller, we put in the new list as the first one, which is smaller, and the larger one as the second element. We get the sorted list, right? We do similarly the same operation for the next list, and then we combine the next 2 lists, the green ones, into the single sorted list. And how do we exactly do that? That's the combined step, and that's what we are going to talk about in the next few slides. So this is the most critical step in merge sort, essentially, the combined step. How do we combine 2 sorted lists to get the final sorted list? One thing to note here is that how the divide phase goes top down while the combine phase comes back up, bottom up. Now let's take a look at the code for the dividing part, and that's pretty straightforward here. So line number 3, that's our base case. And if the list is empty or it has only one item, that we know that it's already sorted. Lines 6 till 8 is the divide step. We find the middle, and then from the midpoint we slice the list into a left half and we slice the list into a right half. Then in lines 10 and 11, these ones, these are conquer step. We recursively sort each of the half, so we get the sorted left and the sorted right, and then we call the merge step to combine these two sorted halves. That merge function is where the real work is, and we'll write it next. Before we write that, here's the core challenge. Given two lists and they are already sorted, how do we combine them into one sorted list? So for example, there's a blue list and there's a green list. How do we merge them? And the answer should be 2, 3, 5, and 6, 8, and 9. And the key insight is pretty simple. The smallest unmerged item is always, sitting at the front of the two lists. Since both lists are already sorted, we just need to compare the two fronts of these two lists and pick the smallest one. So for example, we compare the front of blue list, which is 2, with the front of green list, which is 3. So 2 is smaller, we pick that, and the blue list now has just 2 items, 5 and 8, to compare to the green list. And the new front for the blue list is going to be 5, and since we already picked 2, 3 was remaining behind. The new front, well, the old front actually, is still 3 for the green list. And now then we compare 3 and 5 and so on. We do this using the two-finger technique. 2 fingers, basically they are 2 pointers. One is the blue pointer, which you see, that's specified with the ith index, I index, basically variable called I, and the green pointer is represented by a variable called j, and we start from the 0th index for both cases. Now here's the deal, basically. We compare the values at both pointers and take the smaller one and put it into a new list called result, and then move that pointer forward. For example, so we compare I and j, and I is 2, the item at I is 2 and the item at j is 3, and we know that 2 is smaller than 3, so we take the value 2 and put it in the result and move the pointer forward, which is the blue pointer. At this point we repeat the step. Now comparing 5 and 3, 3 smaller, we choose that and move the green pointer forward. And now we compare 5 and 6, 5 is smaller, we pick that. Whatever item is smaller, we forward that pointer. Basically now we're going to move the blue pointer forward. Now we compare 8 and 6. Which one is smaller, you think? So 6 is smaller, we are going to forward this, increment this green pointer, and that will point to 9. So basically values which are grayed out, they're already picked from the list, and we will never refer to these again in this merge step at least. And now we compare 8 and 9. So since 8 is smaller, we pick that, so it's removed from the list. The left blue list is completely empty, and we have got a bunch of items, potentially at least one. It could be empty also, but here we've got at least one item remaining in the list. So we know that all of these items are going to be larger than whatever our result contains, basically. So all we do is we pick this entire thing and we just simply go and append everything at the end of that list. So we combine this remaining list with that list, and we are done there. So we have successfully merged 2 sorted lists together. So this is basically 6 comparisons for 6 elements. That's O of n. Each element gets touched exactly once. So that's why this algorithm is so efficient. Let me state the algorithm more cleanly. You start with the pointers at the beginning of both lists, that finger technique, and then you compare the elements at both pointers, and then you take the smaller one and copy that into the result. Then you move the pointer forward and you repeat. Once the list runs out, you just dump whatever's left from the other list into the result. All right, your turn. I want you to merge the blue list and the green list by hand. Fill in this comparison table, and what do you compare at each step? What do you take? Which pointer moves? And pause the video and actually do this on paper. You'll thank yourself during the exam. So let's walk through it. Step 1 versus 2, the blue arrow and the green arrow. 1 is smaller, we pick that. Now it's 2 versus 4. The 2 is smaller, we pick that. Our j is incremented to 1, our I is already incremented to 1, and the result is at this point 1, 2, and 3. Actually 1 and 2. So now we compare 3 and 4. 3 smaller, now it's going to be 1, 2, and 3. And since 3 is smaller, we increment the pointer. So I think here these notes need to be updated a little bit. They're showing the result being copied, the value being copied in the result in one step ahead, basically, which we do not want. But the process is the same exactly. So now we compare 3 and 4. The item, basically, the smaller value is 3. We copy that into the list, and now we compare 4 and 8. 4 gets copied, then we compare 7 and 8. 7 gets copied, and then basically this list gets emptied. Here there's a bug, it doesn't show empty, but it's empty at this point. And the only item that's in the green list, that's 8, we copy that as it is, and we get our final list. Now let's turn that into Python code. On line 2, we start with the empty result. And lines 3 and 4, they are setting up the pointers. Each I is for the left side, left list, and the right j is for the right portion of the list. The while loop on line 7 basically is going to keep running as long as both pointers are in bounds. Inside, basically on lines, for example, 8 through 12, we compare the left item, which is under the pointer, and the right item, which is under the pointer, and check which one is smaller. So if the left one is smaller, we append that into the result. If right one is smaller, we append that into the result and increment its index, essentially. And we keep on going, doing that in a loop. And then in line number 16 and 17, we just dump whatever portion of the halves was remaining, basically. So that's basically how the merge step works. It's pretty simple, straightforward, and elegant algorithm at this point. So now this is the complete merge step. We already saw the merge algorithm in the previous slide. Basically, merge sort handles divide and conquer logic, and it calls merge, line number 10, to combine the two sorted lists that it had sorted in line number 8 and 9. Quick check. What's the base case? A list of a 0 or 1 item, it's already sorted, so we just return it. What do we divide? We divide the list in roughly half, so that's essentially the length of array divided by 2. Okay, where's the hard work? Well, the merge step, as we saw, is the critical algorithm in this whole thing, basically. Combining two sorted halves is where all the action is. The big O is n log n. Let's do one more trace. We're merging 27, 38 and the list 3 and 43. So these are two lists we need to merge, and they're sorted. That's why merge works, basically. Essentially, initially we have I, which is the pointer for the left list. and j, which is the pointer for the right list. We compare 27 and 3, 3 smaller. We take 3 and put it in the result. The j becomes 1 because it was the smaller from the right list. And then what we do is we compare 27 to 43, we take 27 and then move the I forward and put that into the result. And we keep on doing that until we are done. So why merge sort is faster? Why is merge sort n log n essentially? Here's one way to think about it. Imagine the recursion, and we saw that it has levels basically. At the top level we have n elements, and as you go down the next level, that is going to become a group of 2 items with n by 2 elements each in each group, and then that becomes essentially 4 groups of n by 4 elements each. At each level, if you sum these elements, you'll get n items exactly. So at level 1 there are n items. At level 2, if you sum the number of items in all of the groups, you'll still get n by 2 plus n by 2, you get n items. At this level you also get n items, and you keep on going down. At the lowest level, it's going to be a list of 1 item, so there are going to be n lists of 1 item. So again, at each level there are going to be n elements exactly. And how many levels are there? There are log n elements, log n levels basically. So that's why the total number of steps is going to be log n. That's the total number of levels multiplied by n items basically. That's the n number of steps in each level. So that gives you n log n, which is the total number of steps it requires to do, merge sort. On the pro side, merge sort is really fast and log n guaranteed, no matter what the input you give it. It also is a stable sort, meaning equal elements keep their original order, and the performance is predictable. No nasty worst cases. On the bad side, basically, it uses extra memory because we need to keep creating new lists to during that merge step. That result that we put our items in, that's a new list every single time. Python's built-in sort and sorted use timsort, which is a heavily optimized version of merge sort. So the algorithm that you learned is the real deal, basically. Divide and conquer beyond sorting. Well, so far we've been using divide and conquer on flat lists, but some data is naturally recursive. It contains smaller version of itself. Think about nested folders in a file, or JSON responses from an API or HTML documents. A folder contains subfolders. A JSON object contains nested JSON objects. And when the data itself is recursive, recursion becomes the natural tool to process it. Here's a real-world example. At the top, from line number 1 till 11, this entire thing. So this is essentially a deeply nested dictionary. It's a dictionary inside dictionary inside dictionary. So look at the credentials here. So that is nested inside the database dictionary, and database dictionary is nested inside the app dictionary. And now look at the function in line number 13. So what this does is it's going to take the top level dictionary, and then it's going to find that key even if it's nested deep inside any level, right? And in line number 14, what we are doing here is we're looping through each key value pair at the current level. Line 15 checks if we have found the target key, and if we found the target key, line number 16 returns the value. But interesting part is line number 17 and 18. Now this is instant thing basically. So what this does is, if the value itself is the dictionary, then we recursively go into it and we search deeper. So this is the recursive call if it's a dictionary. So find key on this dictionary for the value for the key port, it returns the value 5432, and you can see that this key is nested, is buried deep inside this dictionary structure. It's not straightforward out in the open. So let's trace find key config, and the key is basically port. We start with the key app at the top level. inside app, the first key is name, and that's not port. We skip it. And then we hit the database, which is another dictionary. So we recursively go inside it into another deeper level. So inside database, we see host. That's also not port. We skip it. And then the next key is going to be port. We find it and then we return its value, and that's pretty much it. Notice that a flat for loop could never handle this because you don't know how deep this nesting goes. So recursion handles this arbitrarily depth very, very naturally. So here's the second example. It's extremely similar to whatever we have done so far, and the way that we search for keys in the dictionary. And the structure is also very similar to another example that we did in the previous class. That was the flattening of the lists, basically. So the structure is exactly very similar. It's a nested dictionary of dictionaries, but the thing that we need to note is that file is represented with a tuple, and the tuple is the first item index, that is index 0. We have the name, and the index 1 we have its size. That's the only thing that you need to know at this point. So if we look at the data structure at the top, each folder has a name, a list of files, and where each file is a tuple of names again, and a size, and a list of subfolders essentially. So this is the name of the folder, it has files, and then it has subfolders. And then this can recursively go on for a very deep level. The function on line number 16, which is the total size, it does two things. Line 17, it basically sums up all the sizes of all files in the current folder, and the loop on line number 18 recurses into each subfolder and add its sizes. So basically this is a recursive call. Running this on our example structure is going to give 48, and that's the total across all folders and subfolders. All right, so now there are two questions students ask about this code. First, where's the base case in this recursive call? It's actually implicit here. When a folder has no subfolders, the for loop on line 18 simply returns 0 times. In this case, since we have isolated the code, the lines are a little bit off. So we are talking about this line number 3 here, but line 18 in the original previous code here. So if that's the case, if this for loop runs 0 times, we simply return the size of all the files, and that's it. So that's the base case essentially. We don't write an explicit if statement. The real idea for the base case is that you have a termination point and you don't go on forever. And the second question that comes up in the mind of students is, there is a for loop. Isn't this iterative code? Why is this recursive? So that's a good question. The loop iterates across siblings, the subfolders at the same level, but inside the loop, there's a recursive call total size, which is recursively being called on each single subfolder. So there are many recursive calls for each subfolder if there are many subfolders in a folder. So it basically recurs downwards. This loop handles breadth, and the recursion handles the depth. So let's trace this on a tree diagram. So this is what a hierarchy of a file system looks like. We start at the root. There are files, let's say there are total 8 files here. Now we loop over its two subfolders, source and docs. Source has 17 files, and it has one subfolder called tests. And test has only files, it has no subfolders at all. So what we do is the loop that we saw in the previous slide that runs 0 times, which means that no further recursive calls are made. So we immediately return the total size, which is the total count. In fact, in this case, we are counting the number of files, and back to the previous call. And then we go to the doc. So basically, the test returns its result to source src, and src returns its result to root. And then we go to the docs folder and recursively go down. But this is, again, incidentally, it doesn't have any subfolders. So this is going to be considered as the base case, returning all of the files and then to the root, and then we add the count of source and docs together, and then we get the total number of files in the root. And what do you get here? So basically this is going to be 8. 8 plus 17, that's 25, and 25 plus 8 is and plus 15, that is 48. So once again, we see that the divide and conquer pattern here. Divide, basically each subfolder has its own sub problem. Conquer, we recursively compute the size or the number of files, the count in each subfolder, and then in the combine step we sum everything up together. And this is actually how the du command works on Linux. The disk usage, basically, is exactly the same algorithm. All right, your turn. So same pattern as total size, but instead of summing the file sizes, you're counting the total number of files. The hint is in the previous tree that we just did. You need to fill in these two blanks here. And again, the hint is for our structure. So total size sum, f of 1. So what is f of 1? If we take a look at our data structure again, so basically each file has two components in a tuple. The first one is the 0th index, that's the name of the file, and the second index, the first index number 1, that's the size of that file, basically. So that's what it's talking about here. So pause the video, give it a try, and let's see if you can do it. So basically the first blank is going to be the length of folder with the key 5. So basically that's the list of all the file tuples that's inside this. And the second blank is going to be the recursive call called count files, because now we are operating on all subfolders, and each recursively goes into each subfolder. Running it gives us a total 5 files, a same divide and conquer template, but just a different operation. Okay, practice time. Well, I want you to close your notes right now and try writing the merge sort completely from scratch. No peeking, give yourself 5 minutes. It doesn't have to be perfect. The attempt itself is just for building understanding, and after 5 minutes you can check yourself. Did you get the base case right? Did you get the divide step right? The merge function, did you get that right? And most people, that they struggle with the merge function, and it's completely normal, so you need to focus your study there. Summarize. Let's bring it all together. Merge sort uses divide and conquer. You split the list, recursively sort each half, and then merge them back together. The merge step is going to be the clever part. And another key point that we need to take here is n log n algorithms. They absolutely crush n squared algorithms, and we do n work at each log n levels. In n squared algorithms, you do n work in each n levels. So n into n, that becomes n squared. Here we do n work at each level, but there are only log n levels, so that becomes n log n. And the divide and conquer works on recursive data too. Obviously, nested dictionaries, file systems, JSON, HTML. If the data is recursive, recursion is the natural tool. Here's a general template, and I want you to memorize this skeleton. The base case on these lines, the second line and the third line, if the problem is simple, return the direct solution. And then in line which is highlighted at this point, this is the division problem. Basically, we split the problem into pieces. It can be 2 pieces, 3 pieces, how many pieces you want, but each piece has to be roughly equal size. That's the key here. And then these 2 lines, they solve each of the pieces. So for example, if you have only 2 pieces, you can solve the left and you can solve the right. But if you have many pieces, let's say 10 pieces, then you'll probably use a for loop to solve each of the piece, like we did in the file system example. And once you have solved each piece, then you have to merge all of the pieces together. So binary search, merge sort, file system parsing, they all follow the same skeleton. So for homework this week, part 1, you need to implement merge sort from scratch without notes, and add a print statement to show every split and merge step. And the part 2 is going to be essentially write a descending merge sort. only one comparison is going to need to change basically. And also write is sorted using divide and conquer. So that tells whether an array is already sorted or not. You need to implement count files and then find all keys for recursive data. And part 4, that's optional bonus challenge basically. That asks you to merge k sorted list using divide and conquer and count inversions by modifying the merge sort. So I'll recommend essentially starting with parts 1 and 2. Next week, we'll be covering 2 powerful extensions of recursion: memoization and backtracking. Memoization is essentially remembering answers that we have already computed so that you don't have to redo the work. It makes, for example, Fibonacci almost instant. And the backtracking is about exploring possibilities and undoing bad choices. It solves mazes, it solves Sudoku puzzles, and n-queen problems. And that's a wrap for lecture number 8. There are 3 words to remember: split, sort, and merge. Practice the merge by hand on paper with real numbers. That's the part that trips up people, and it's the part that clicks once you have done it a few times. See you next time. Bye bye.